Okay, so I'm going to try and take this from the standpoint of going to more or less a fundamental definition of what a function is. And so before we do that, we have to look at what a relation is. Now, if we can make this definition that it's a set of any ordered pairs. So if we have an ordered pair of 1, 2, or 4, 3, or 5, 6, you know, various points like 1, 2, 4, 3, 5, 6, and 0, 6. We call that a relation because there's we have a value in the first place, the x-coordinate, is associated in some fashion with the y-coordinate. We call the set of the first numbers, of the first components of this thing, as the domain. And so with a function now we're talking about having something from the domain that's associated with another number, and the set of those numbers we're going to call the range. And so the set of these output numbers, so to speak, are going to be the range. And so the thing to remember about these is that these elements are elements of a set, and they're listed once. And so if we look at this, we have, okay, 1 is associated with 2, 4 is associated with 3, 5 is associated with 6, and 0 is associated with 6 as well. So think about one relation could be, let's say, car manufacturer with car model. So I can say if my ordered pair is model or manufacturer and then model, I could have ordered pairs like Chevy Impala, Chevy Nova, or Honda Accord, Honda Civic, you know, that kind of stuff. So I certainly have pairs where if I give you a manufacturer, you can tell me the models that it's associated with, and that's just a relation. We can do it the other way around too. If I say, okay, my domain is going to be the set of car models, and if I then say Accord, you would say Honda, you know, or F100, then you say that's Ford or truck, that kind of stuff. So relations basically just make some sort of association between two components. The first one is the domain. That's usually thought of as the input of a function, and or of a relation, and the range is what it's associated with, which is more or less the output. Okay, so we'll talk about functions now in this context, where a function is a rule that assigns a value in the domain, each value in the domain, to exactly one element in the range. Now I put exactly in red because that's the thing that distinguishes between a function and a relation, is that a function makes exactly one assignment. So let's say if car manufacturers never named cars the same as a car in another manufacturer, and that's not quite true because there's been car models like Mark 6 and stuff like this that has been in more than one manufacturer. But let's say if it was that way, so Accord would be associated with Honda, or F100 would be associated with Ford. That would be a function, because a car model would be made by exactly one manufacturer. The other way around is not a function, because a car manufacturer makes many models. And so the thing that distinguishes a function is that you get exactly one assignment assigned to each element in the domain. Okay, so if let's say choose some numbers here, 0, 3, 7, and 12, and I assign, and then I have some numbers in my range, 4, 2, 3, 1, make that assignment. Okay, this relationship is a function, or this relation is a function. So I could notate this function as 4 sets of ordered pairs. If I had 0, 3, 7 and assigned these in the range, this would not be a function if I did it in this fashion, where I would assign 7 to both 3 and 12. So that first relation I showed on the first slide and this one is not a function because I have a value in the domain that gets assigned to two values in the range. So that's that is the distinguishing part of the definition of a function. And I'll go back, you didn't quite finish. Okay. Now, the other way is okay. I can take a value in my domain and assign it to a value in the range that is the same as some other value in the domain. Like in this case, if I have 0 and 4 both assigned 1 in the range, this is okay. Okay, this is still a function because it meets that definition that every element in the domain is assigned exactly one value in the range. The values in the range can be reused. Okay, so let's talk about some notation now. You've no doubt have seen functions represented as f at x before. And so the f is the name of the function, all right? We use letters as names of variables, but we can also use them as names of functions. And in this case, f is not a variable, it's a function. X is the value from the domain that gets assigned by the function to some value in the range. And so here's a subtle difference. F is the name of the function. So we can say the function in this example is f. We don't have to say f at x, okay? But if I say the value of f evaluated at x is f at x. Okay, so when I'm talking about the value of a function, you always put the argument there. We sometimes call that x the argument. So catch the subtle difference here, where f is the name of the function, f at x is the value of the function. Now, some people say f of x, and some people say f at x, and if you're like me, you say it both, and you say it fast enough where you can't even tell if you're saying at or of. Okay? So either one is fine. I don't even know that one predominates over the other. All right. So f at x is a value, and it's time for our morning music again. Okay, so let's have some examples here. So f at x equals 2x plus 1. Now, on a simple function like this, I can give you a number and you can probably do it in your head what the value of the function is. But what I want to kind of suggest is that you get into the habit of writing your functions like this. So if I want to evaluate f at 0, what I'm going to do is I'm going to write out the definition of my function, but instead of writing anything where x goes, I'm going to draw some parentheses. And then after I finish doing that, then I'm going to drop in what the value is and then compute the value. So it's actually 3 little mini steps. First one is to write out the definition of the function. Second step is to drop in whatever the argument to the function is. And then the third one is to evaluate it. On something like 2x plus 1, this is trivial. This is almost not worth making a distinction between these things. But it helps you when you have things like negative numbers. Okay, so this one doesn't help you all that much, but you can see my pattern here is that I'm just going to drop in a negative 3, and it doesn't matter that this 2 is positive or negative. I'm not even thinking about that. I'm just dropping it in. Now I can think about it. 2 times negative 3 is negative 6, plus 1 is 5. Now, I can take expressions and other variables and drop them in the same fashion. So if we say, what's f at t? Well, f at x equals 2x plus 1, so I'm going to write the form of my function like this. I'm going to evaluate it at t, and so I'll drop in the t, and I get 2t plus 1. Okay, so are we good with this? And this is fairly straightforward. Okay, so let's have a little bit more complicated function and see how this can benefit us. Okay, so 2x squared minus x plus 1, a simple polynomial quadratic function. So I can evaluate f at 1, and so I'll use my process of just writing some variable, writing some parentheses instead of the variable, and dropping in the variable, and then evaluating it. So kind of 3 steps again. Write out the function, drop in the argument, make the evaluation. So here's where it's going to help you. Let's say f at negative 2. Now, we know that we're going to have 2x squared, and that negative 2 is going to become positive, and then we have this negative x. And my guess is that if I gave you 100 of these to do and gave you 10 minutes to do it in, so you're writing fast and furious, you'd probably mess up. I would mess up at least 20% of the time, because just keeping track of signs, you think, oh, negative 2, and you have negative x, so that's, negative 2. Well, it changes, right? It's negative 2. But when you're in a hurry, you make that mistake. So if you do it this way, if you write first the function, then drop in the argument, now do the evaluation, you have it right in front of you. You don't have to think about it. It's negative 2. And so all these things then evaluate rather easily. 2 times 4 plus 2 plus 1 is 11. And it's bulletproof to do it this way. I shouldn't say bulletproof. You have far less of a chance of making a mistake doing it this way than if you do any operations in your head as you're writing these things. And I've said this from the beginning of the semester, I don't think writing costs you any time. What costs you time is when you stop and think. And doing it this way, you have to stop and think less, right? Because there's nothing to really think about until you're actually doing the evaluation, and there all the pieces are laid out in front of you to make it an easier problem than if you're doing it, trying to keep track of it in your head. Okay, so let's look at another function. So 1 over x minus 1, we're going to revisit this function a little bit later as well. So I just write out my function, drop in my 0, evaluate, and simplify. So if I take negative 2, now I have to think about having more than one negative in there, but again, if I write it out just my standard way, drop in the negative 2, negative 2 minus 1 is easy to see, and we have 1 over negative 3, which is the same as negative 1/3. So remember with the slopes, I suggested this as well, that you write the differences in parentheses, that you have a parentheses minus another parentheses over, and just drop in the numbers. Perhaps you've made enough sign mistakes, inadvertent things that you understand perfectly, but you just, make little blunders here and there, that using parentheses in this fashion really increases the reliability of your computations. I can't say that enough. And as many years as I've been an engineer, I have always done it this way. And I've made very, very few computation mistakes when there were dollars on the line and my reputation on the line as well. I've ruined my reputation other ways, let me put it that way. So we have f at 1 now. All right, so we're going to drop in a 1 here, and we get 1 over 0. And so that doesn't evaluate, right? 1 over 0 is not defined. And so it's undefined. And so what this means is that 1 is not in the domain of the function. Go back to the definition. What a function is that we're going to assign every value in the domain exactly one value in the range. Well, we can't do this. We can't assign 1 a value in the range because it doesn't evaluate. So we have to say that that 1 is not in the domain. So numbers that don't compute for us, that we get something other than a real number, we have to exclude from the domains. Okay, so the domain of a function oftentimes is explicit and sometimes it's implied. And in something like f at x equals 2x plus 1. The domain is all real numbers. Now the notation I'm going to show you is, we're going to talk a little bit more about the notation, but this capital R, perhaps you recall seeing it from the beginning of the semester, where that means the set of real numbers. Okay, so it literally reads the set of real numbers. And so that's a perfectly good, valid, compact way to describe a set. Okay, and remember, domains and ranges are sets. The other way is with interval notation. You go from negative infinity to infinity. That's a perfectly good way to do that. If we have our function 1 over x minus 1, we have the domain is all real numbers, except we have to exclude 1. And so there's a couple ways to notate that. The first one in interval notation, and this gets probably more complicated than it's worth. Or at least I always think of this way. I mean, that's a lot of writing for saying, you know, we want to leave out a 1. Right? We go from negative infinity to 1, but not including 1, and we join that with an interval from 1 to infinity, but we're not going to include 1 in either of these two intervals, so it's left out. An easier way is something called set builder notation, and I'll be describing this in a little bit more detail as we go along, but this, for some reason, people hesitate to use this notation, but it's actually, I find, a little easier and more straightforward to write this than any other interval notation or any other notation for a set other than using single symbols like R. Okay, so let's look at this one. F at x equals the square root of x minus 1. What's the domain of this? All right, so you ask yourself, what numbers will lead to another number if I try to evaluate them? So I know that x minus 1 has to be greater than or equal to 0, because what the square root tells me is that I can only take the square root of a positive number or 0, and so whatever expression I have in there has to be greater than or equal to 0. Well, let's solve for x then, and this is a simple solution. It's x is greater than or equal to 1. So that pretty much describes our domain. That pretty much describes the domain. So we can write it as an interval like this. You know, this is nice and compact. It says we're going to start at 1, and we can include 1 up to infinity. And of course, with 1 minus 1 is 0, square root of 0 works. Think of what doesn't give you an error when you put it in your calculator. So if I put anything 1 or more in my calculator into this function, I'll get a number. In set builder notation, now notice how similar it is written to this one up here, where all I'm doing here is the way this reads literally is, okay, so these two read the same. This one, the way you would read it is the set of x such that x is greater than or equal to 1. And I'll break that down for you in the next slide a little bit more carefully. But what I'd like you to do first is find what the domain is of this particular function. Okay, so find the domain. What are all the values of x that lead us to a value of f at x? Equal 3. You know, we'll notate that as x does not equal 3. So it's all real numbers such that x does not equal 3. And this isn't the way you talk in plain English, right? You don't say the words such that. I mean, try using that in an ordinary conversation with one of your friends, and you use the phrase such that. They'll look at you kind of funny, right? But it's the recognized way of saying this in math, where you say all real numbers x such that x does not equal 3. Yes?
If you write it in set builder notation, do you also have to say all real numbers? Or is that
I'll talk about that in just a minute. The answer is no. Okay? So let's go to the notation of domains. Okay, so we'll agree that the domain of that number or that function can't be, that's all real numbers except 3. Okay? Yes?
Well, so do you just try numbers until...
No, what you do is you look at the operation. And so remember I had this one where this was what, 1 minus x?
X minus.
X minus 1. And then let's say we have another function that I just had, 3, or it was 2x over 3, right? 2x over 3 minus x. So the thing that you do, the clues to finding these things with the domain, is look at the operations and say, can I do that with every number? Okay, and so if the operation here is division, can I divide by every number? And the answer is no, I can't divide by 0. So then what I'm going to do is take this expression, so if my function has some stuff, and 2x works for any number, we'll get a nice perfect number, and anything can be in the numerator. But in the denominator, we know that this is not 0. Okay, so what we'll say is 3 minus x doesn't equal 0, and so when does it equal 0? So we'll solve the case for when it does equal 0. Okay, and so that says x equals 3, so I know it's not supposed to be that, so my domain is that. Now with the square root, I can't take the square root of a negative number. I can take the square root of 0, that works, that's 0. Any positive number, so I know that x minus 1 is supposed to be greater than or equal to 0. So I write my expression and the rule that I have. So here's the expression and my rule. All right, and then so this comes out to be like that. Sometimes it's a little bit more complicated, but I mean that's the strategy to use. So let's talk about how we're going to write this as a set now. Okay, you can always use the capital R with the double spine in the back, and that, like I said, literally reads the set of real numbers. Interval notation, we've worked with that, and so you can have unions. In most intersections, you can just make them as a single interval. So it's mostly unions that you'll be dealing with. And then the set builder notation is works like this. The very first, brace reads as the set of. And of course, the x says x there. And then this vertical line is that phrase that you never use in conversation, such that, although you understand what it means, right? And then you write whatever description you want in that second part, and in this case, x is greater than or equal to 0, I guess is the real translation. So what we're going to do is we're going to decide, since this course only deals with real numbers, we're not going to deal with the square root of -1, any imaginary or complex numbers like that. When we have something in set builder notation that has some restriction or some description of x, we're going to assume that that's taken from the set of real numbers. Okay, so we don't have to write, there is a way to write that it comes out of real numbers, and it looks like this, but I'm not going to make you do this, where you can say the set of x such that x is an element of the real numbers and x is greater than or equal to 0. I mean, that's the long version, and we don't need that because we're going to always assume that x is an element of the real numbers, set of real numbers. So don't worry about that part. Okay? If we have no restriction, then just write the set of real numbers. All right? Straightforward enough? Okay, so here's one for you to try. I'd like you to write this domain in set builder notation now. So with this function, write the rules like this. Figure out what the restrictions of x have to be, and then write it in set builder notation. Okay, so what we found was the set of x such that x does not equal 0 or x does not equal -1. And you know, not too long ago I started reading it, you know, the not equal sign is that x cannot be 0, okay, which to me describes a little bit more in the set character than x does not equal 0. X does not equal 0 is really literally the way you say that, but I think its meaning is more conveyed when you say x cannot equal 0, because then you're saying x can be everything except that. Okay, let's go to the movies. Nah, you already went to the movies, so you blew it. Okay, blame it on Ryan. But anyway, you all see something like this, okay? So where you have a sign that says, okay, if your age is under 14, the cost is $5. If your age is between 14 and 65, it's $15. And the age, if your age is over 65, your admission is 10. Okay, so you would expect certain things out of this. Number one is that all the practical ages are listed here, right? I mean, even the impossible ages are listed here. Like -3 is not a possible age, but it's implied here that you're not going to be less than 0, right? But even if you were, it costs you $5. There's no upper bound on it, although I suppose the Guinness Book of World Records might have a listing of the oldest person who ever attended a movie, you know, maybe that would be the upper bound if you're between 65 and 120 or whatever the upper bound of human life is. But you don't necessarily have to do that. But in all the ages that we're interested in, we know what the cost of the movie is. And we know it, and we only expect it to be one value. So my phrasing on the partitions between these things have to be fairly careful. So if I say up to and including 14 is $5, and then from 14 to 65 is $15, what would it be if I was, you know, I'd go up to the window and say, I want to buy a 14-year-old ticket. They say, well, that's $5 or $15. Well, that's absurd, right? You want it to be a function where when you give an age, you get exactly one value for the range, or in this case, for the cost. So mathematically, we have a way of writing these kinds of signs, and it's basically using our set builder notation and our functions together to get a function, and we call these piecewise functions. All right, so a piecewise function, let me show you how to make, in standard mathematical notation, this particular movie admissions policy or costs in piecewise function notation. So remember a function, okay, it has a definition for the segments of its domain. And so if the age is the domain, if all the practical ages of a person is the domain, I have segments of those of that domain, under 14, between 14 and 65, and over 65. That's going to be part of my piecewise definition. And so I'm going to say A is my age. So I'm declaring my variable here. A is my age. My domain is A such that A is greater than or equal to 0. That's just because people aren't negative years. So that's my total domain. But I have segments of the domain as being, you know, those segments divided by 14 and 65. So I just write those like this. That's the expected notation, right, to indicate what pieces of the domain they would be. And let me say C at A is my function. So this is the cost of admission. I'm going to say C at A. I've defined that. And then the way I'm going to write the whole function is I'm going to use this, this brace like we used it for sets. We're suggesting that this is a set of equations now where the value of it is going to be 5. It's going to be 5 when I'm less than 14. It's going to be 15 when I'm between 14 and 65, and it's going to be 10 when I'm over 65. Now, oftentimes you see this written not exactly like this. You'll see instead of the comma, and sometimes you won't even see the comma, but it'll be written like this, and maybe it's a little easier to understand if, with the word if in there. Okay, so it looks like kind of a mess, but you know, it's a very uniform, standard way to write a piecewise function. So, you know, with this movie thing, you know, that's a pretty easy example of why we need piecewise functions. But the piecewise functions don't necessarily have to be that we have a value here. We can also have an expression. So for example, if I wrote this, where I substitute the, if I substitute A for 5, what this is saying is that if I'm under 14, my age is my admission price, right? So I look for, if I want to calculate what's the value of somebody going to the movie at 10, you say, okay, this is the rule that applies, and so your function equals A. So the function here, C at 10, equals 10. All right, so we can have any kind of algebraic expression in here that we want. It doesn't have to be a constant. You know, it can be any expression. It's just that what we do when we read this is we look for what piece of the domain are we talking about, and then we evaluate that at that piece of the domain. So let's go through a couple examples here. Okay, so just kind of recap here. The second part is the part of the domain. The first part is the value of the function. And it can be an expression. Okay, so let's look at this function here. The absolute value, we know what the absolute value is. The absolute value of 5 is 5. The absolute value of 5 is 5. Is that what I just said? Absolute value of -5 is 5. So in other words, we take the size of the number, or we take the distance from the number of the number to 0, or we take the positive value of the underlying number, any of those things. We can actually define it as a piecewise function, and we say, okay, the notation is the absolute value. I can define it like this, as a piecewise function. So this means when I have x is less than 0, my value is the opposite sign of my value. And when x is greater than or equal to 0, it's just the value itself. Okay, so let's see how this plays out. So here I made a little tiny mistake. I'm really talking about when x equals -2. Okay, which of the rules corresponds to when x is -2? Well, we look at the domain statements, and one of them is x is less than 0, the other one is x is greater than 0. So -2 is less than 0, so it's the first line that applies to this function, right? So we're going to look at this line is telling us what the description of the function is, because this is true, so this is what our function is f at x equals -x. All right, so then let's drop that in like I had before, where we're going to say f at -2 is negative, and then put our parentheses, drop our -2 in, -2 is 2. So it gives me the positive value, even though that looks a little deceptive, doesn't it? I'm going to expect, if I just take a beginning glance at this, that these values are going to be less than 0. No, because x itself is less than 0, and so if we have negative, then we get the positive version. So what this is saying, in a little bit more descriptive terms, is that we're going to change the sign if we are less than 0, and we're going to leave the sign alone if we're greater than 0. Everybody okay with this one? Yes.
I'm confused about the whole absolute value part. Like, why don't you plug it in there?
Well, what I'm doing is I'm saying, let's say I didn't have all those other values, those other definitions of absolute value. I'm going to define absolute value as this. Okay, so I'm making a definition for the absolute value.
Okay, so you don't need.
No, what I'm suggesting that this is the absolute value function. Okay, it's just like when I say, you know, f at x equals 3x. This means I'm defining this function as 3x. Okay, and so what I'm saying is my absolute value of x I'm defining as that piecewise function. Okay, so yeah, certainly if I have a definition of absolute value of x, I don't need to, you know, redefine it again. But here is a piecewise definition, and the nice part about this is that there's really no description necessary. It's simply you know, the way that we partition up a domain and we make an algebraic definition. So there's no description beyond this that's necessary. Okay, so we know the absolute value of negative 2 is 2, and that's what this whole exercise shows us. Now here's one, and I make kind of a funny little mistake here. If I take g at x equals those two descriptions, so when x is less than 4, g at x is 2x plus 3. And when x is greater than 4, or equal to 4, it's going to be x minus 5. So what I'm really talking about is the same function here. Now notice I slip over to f here, and what I really mean is g, or what I'm going to ultimately do is correct this to just f at x. I think I might do this. Yeah, so I'll correct it right now. Okay, so I'm saying f at x equals this definition. So what does f at 0 equal? So let's look at the definition. The definition is when x is less than 0, and in this case x is 0, then I'm going to use the expression 2x plus 3. So I'll take my 2x plus 3 is simply going to be 3. So if I take f at 7 now, I look at my domain, and no, x is not less than 4, so I'm not going to use that line, but yes, 7 is greater than or equal to 4, so I'll use this definition, and so I'll just pop in 7 minus 5, and I get 2. Now, the part that you always have to be careful about is what are the boundaries of these things? What are the borders of these partitions? And so here, I'm going to evaluate f at 4, and I see that 4 is not less than 4, but 4 is greater than or equal to 4. So I'm going to use the second definition of my function and say 4 minus 5 is negative 1. Is everybody good with this? Okay. What I'd like to do now is go over to do this. But the point that I'm going to reach here is how do you graph a piecewise function? Okay, so kind of hang in there with me. If we were to graph f at x equals 2x plus 1. Now you only have to take 2 points and draw your line, but if I were to make a table of values, I'd get this, and so I could sketch a graph that looks a little bit like this, where my x-intercept or my y-intercept is 0, and my x-intercept is going to be, what is that, negative 1/2. Okay. So if I do this now with my absolute value function, and I make my table, I have negative 3 equals 3, negative 2 equals 2, negative 1 equals 1, 0 equals 0, and then 1 equals 1, 2 equals 2, and 3 equals 3. So when I make my drawing, it's going to look like this. Okay, so what I want to do is I want to make the graph of a piecewise function that's defined this way, where it's negative x is less than 0, and it's going to be 2x plus 1 when it's greater than or equal to 0. Now, I already know what the graphs look like when I'm making this thing over all real numbers, but what do I do with my piecewise definition? What I'm going to do is I'm going to make the graph up to the boundary of the part of the domain that I'm interested in, and then when I go into the next part, I'm going to just make the graph of the function there. So first thing I'll do, let's say, is make up some values. And I'm going to use the same, negative 3 to 3 kind of thing. And notice when I'm at this point, this negative 1 is still the absolute value, so that's 1. But at 0, 0 is actually x is greater than or equal to 0. So I'm going to use this definition of my function, and I'll find that f at 0 is actually going to be 1. And so I'm going to plot these lines, and I'm going to pay attention to what happens at the borders between them. So if I make my graph, when x is greater than 0, that's going to look like this, and when x is less than 0, it's like this. Now, the point where it flips over, I certainly can define this. I mean, the absolute value is defined at 0, but it doesn't, this particular function doesn't include that because f at 0, as I said, was 1. So I'm going to go all the way up to what the boundary of my domain is. In this case, the boundary is 0, but I'm going to put an open loop indicating that I'm heading towards there, but I'm not actually getting there. So if I take f at negative 0.00001, I'm going to get something very, very close to 0, right? But if I take 0 or anything more, it's going to look like what my other function, what the other part of the function looks like, which is 2x plus 1. So what's the practical way of going about doing this? And sometimes this gets kind of hard. So one of the ways that you can do it is, I'm an advocate for using pencil in math, right? So what I can do is I can say, if I'm going to start with the first part of the function, okay? And I know that function, the absolute value function, looks like this. And then I'm going to graph on top of it the other part of the function, which is 2x plus 1. And so that's going to look a little bit like this, right? Okay, so now I'm going to take my eraser and I'm going to say, when I'm below 0, I'm this function. So I'm going to erase my other function. And then when I get to 0, it's not going to include that because that's not part of what I'm going to do. And now, since this stops at 0, and this one is now the function that applies, or the part of the function that applies. It is actually defined when x equals 0. It starts there, so I'm going to put a dot, and I'm going to erase the other part. Okay, so that's how I get my graph. Don't worry about, so much trying to get this right initially. Make yourself a sketch of everything being overlaid and just erase the parts that don't apply. Okay? And I'm going to leave this